The universe is a gallery of beautiful horrors. We are about to journey far beyond our comfortable blue planet into realms where the laws of physics are pushed to their breaking point. This is an exploration of the universe's most extreme environments, places of unimaginable pressure, impossible cold, and violence on a cosmic scale. By the end, you will possess a new understanding of just how strange and hostile the cosmos can truly be. We will find oceans that boil under alien suns and wonder planets cast adrift in eternal night. So, what do you think it takes for a world to be called truly alien? Our journey begins with a world that redefines the very concept of an ocean. Orbiting a dim red dwarf star about 40 light-years away, Gliese 1214b is a super-Earth, a planet several times larger and more massive than our own. But its true nature is revealed not by its size but by its composition. This is a water world. Its entire surface from pole to pole is a single, uninterrupted global ocean. There is no land, no beach, not a single rocky shore to break the monotony of its endless horizon. Yet to call this a simple ocean is a profound understatement. The conditions here are so severe that water cannot exist in any familiar state. The planet orbits so close to its star that its surface is searingly hot, while the immense weight of its own global ocean creates pressures hundreds of times greater than the deepest trenches on Earth. Here, water enters a bizarre fourth state of matter known as a supercritical fluid. Imagine steam and liquid merging into one. The water becomes a thick, soupy, superheated atmosphere that clings to the planet's surface, a roiling, murky abyss where the distinction between ocean and sky vanishes entirely. Light from its red sun would penetrate only a short distance into this oppressive gloom, leaving the depths below in permanent, crushing darkness. It is a seascape of unimaginable scale and strangeness, a place where our most fundamental understanding of an ocean simply does not apply. Yet that alien ocean is not the only place where familiar substances become unrecognizable. Closer to home, within our own solar system, a storm of unimaginable riches is falling. The ice giants Neptune and Uranus are worlds of profound, cold, and furious winds, but their true strangeness lies hidden deep beneath their blue methane hazes. Within their atmospheres, pressures build to millions of times greater than what we experience on Earth's surface. In these crushing depths, something extraordinary is believed to occur. Vast quantities of methane, the simple molecule that gives these planets their hue, are torn apart by the intense pressure. The hydrogen is stripped away, leaving behind raw carbon atoms. And under such extreme conditions, carbon does what carbon does best. It crystallizes. Scientists theorize that deep inside these frigid giants, solid diamonds form, not as rare gems tucked in stone, but as a constant, glittering precipitation. Imagine a hailstorm of diamonds, each crystal potentially as large as a pebble, falling for thousands of miles through a slushy ocean of water, ammonia, and methane ices. This is not science fiction. Laboratory experiments here on Earth have recreated these extreme conditions using powerful lasers to shock plastic, which is rich in carbon and hydrogen, and observing the formation of nanodiamonds. The models suggest this diamond rain would sink slowly toward the planetary cores, a continuous, dazzling shower in the eternal darkness. It is a phenomenon of breathtaking beauty and violent physics, a reminder that even within our celestial neighborhood, nature's extremes can forge treasures from the most common of elements. But the universe's cruelty is not limited to worlds bound to a star. Some planets are sentenced to a fate far more desolate. Cast out from their home solar systems by gravitational chaos, they become wanderers of the interstellar void. These are rogue planets, and they exist in a state of perpetual exile. Imagine a world where the sun never rises. Its sky is not a canopy of blue or a tapestry of stars at night. It is an eternal, unbroken black. Without a nearby star to warm it, its surface temperature plummets to just a few degrees above absolute zero, the coldest temperature possible in the universe. The very air, if it had any, would freeze solid and fall as snow onto a landscape of everlasting ice. It is the definition of a frozen tomb, a lonely monument adrift in the galaxy's silent spaces. Yet within this profound darkness, a flicker of possibility remains. Deep beneath that icy crust, heat might still stir. The decay of radioactive elements in the planet's core, or the relentless squeezing from the gravitational pull of a large moon, could generate enough warmth to maintain a vast global ocean trapped between the frozen shell and the rocky interior. This creates a bizarre paradox. On the surface, an airless world locked in a deep freeze more severe than any Antarctic winter. But below, in that sunless sea, liquid water could persist for billions of years, sealed away from the void above. In such a lightless abyss, life as we know it could not rely on photosynthesis, but around hydrothermal vents on the ocean floor, fueled by chemical energy and geothermal heat, ecosystems might cling to existence in total darkness. A rogue planet, then, is not merely a frozen rock. It is a potential ark carrying a sealed, hidden ocean through the galaxy, a secret biosphere traveling in absolute silence and perfect night. These wandering worlds are not the only exiles in the dark. The galaxy itself can fling entire stars into the void with unimaginable force. At the heart of our Milky Way, a monster lies in wait. It is a supermassive black hole named Sagittarius, a star, a gravitational titan containing the mass of 4 million suns. Its presence creates a chaotic dance of stars orbiting it at ferocious speeds. And when a binary star system, two stars locked in a mutual orbit, ventures too close, a cosmic slingshot event of staggering violence can occur. The black hole's immense gravity can tear the binary pair apart. One star is captured, doomed to swing around the black hole on a new, tight orbit. The other, however, is not swallowed. It is violently ejected, catapulted away from the galactic center like a stone from a sling. These are hypervelocity stars, and they achieve speeds that defy belief. Some are clocked racing through the galaxy at over 1 million miles per hour. At that velocity, you could travel from Earth to the Moon in under 15 minutes. These stellar projectiles are not following the serene, circular paths of most stars in the galactic disk. They are on a one-way trip out. As they hurtle through the thinner gas of the galactic halo, the region surrounding the main disk, they plow through the interstellar medium. The effect is similar to a speedboat cutting through water. The star's fierce radiation and magnetic field push against the sparse gas and dust, piling it up into a glowing, arcing wave ahead of it. This is a bowshock, a luminous testament to its incredible speed, a beacon announcing its solitary and irreversible journey. These stars are destined for a profound loneliness. Their speed is so great that they will eventually overcome the Milky Way's gravitational pull entirely. They will break free, becoming true intergalactic travelers, shooting through the vast, empty spaces between galaxies for billions of years, carrying the light of a lone sun into the endless cosmic night. Our own solar system holds a stark warning of what happens when a world loses its balance. Just next door, shrouded beneath a perpetual blanket of thick, yellowish clouds, lies Venus. Often called Earth's twin due to its similar size and rocky composition, this world is anything but a sibling. It is a vision of hell, a planetary-scale catastrophe. The surface of Venus is the most hostile environment we have ever directly observed. First, the pressure. The atmosphere is so dense that standing on the surface would feel like being submerged under nearly 1 kilometer of ocean water. Every square inch of your body would be crushed by a force 92 times greater than the air pressure you feel right now. Then there is the heat. A runaway greenhouse effect has trapped solar energy with terrifying efficiency. The average surface temperature is a constant 872 degrees Fahrenheit, hot enough to melt lead and even some metals like zinc. This heat is so uniform that there is little difference between the equator and the poles or between day and night. The planet is in a state of perpetual, blistering oven. And those beautiful, reflective clouds that give Venus its brilliant appearance in our sky, they are not made of water vapor, they are composed of corrosive sulfuric acid. This acid rain forms high in the atmosphere, but in the incredible heat below, the droplets completely evaporate long before they could ever touch the scorched ground, creating a bizarre cycle of rain that never falls. Venus stands as our solar system's ultimate cautionary tale, a clear and present example of a greenhouse effect spiraling completely out of control. It shows us that a world with the right ingredients for life can, through a chain of events, transform into an unforgiving furnace. The transformation of Venus is a stark reminder of a world turned hostile, but in the frigid outer reaches of our solar system, a different kind of geological violence hints at hidden worlds of possibility. Orbiting the gas giants Saturn and Jupiter, small, icy moons harbor some of the most dynamic and surprising landscapes we have ever seen. Their surfaces are not scarred by fire and lava, but sculpted by a phenomenon known as cryovolcanism. These are ice volcanoes. Instead of erupting molten rock, they blast plumes of water, ammonia, or methane into the void. On Saturn's moon Enceladus, this process creates one of the most breathtaking sights in the solar system. At its south pole, a series of massive fissures known as the tiger stripes scar the icy crust. From these deep cracks, enormous geysers erupt, jetting water vapor and tiny ice particles hundreds of miles into space. This material forms a faint, shimmering ring around Saturn itself, a celestial fountain born from a tiny, frozen world. The energy driving these eruptions does not come from a molten core of rock, but from the immense gravitational tug of Saturn. As the moon orbits, Saturn's gravity flexes and squeezes its interior, generating enough heat to maintain a vast global ocean of liquid water trapped beneath an icy shell perhaps 20 miles thick. Those spectacular plumes are direct samples of this hidden sea, venting into the vacuum of space. Jupiter's moon Europa likely shares this secret. Its surface is a cracked and jumbled labyrinth of ice, suggesting a similarly active interior and a subsurface ocean that may contain more liquid water than all of Earth's oceans combined. Here, the extreme environment is not one of heat but of cold and pressure. The eruptions are not fiery but frigid, yet within that darkness, warmed by the same gravitational forces and possibly by hydrothermal vents on a rocky seafloor, the conditions for life as we know it could exist. These cryovolcanic plumes, then, are more than just geological curiosities. They are vents from a sunless sea, offering a tantalizing pathway for future missions to taste the chemistry of an alien ocean without ever drilling through the ice. In the profound cold of the outer solar system, the most promising environments for life may be hidden beneath ice, announced to the universe by silent, glittering eruptions against the blackness of space. The silent eruptions of icy moons hint at hidden oceans, but some cosmic objects announce their presence with a violence that can be felt across the galaxy. When a massive star dies in a supernova, its core can collapse into one of the densest objects in existence, a neutron-star. A teaspoon of its material would weigh as much as a mountain. But for a rare few of these stellar corpses, the story does not end there. They become something far more terrifying, a magnetar. Imagine taking the entire magnetic field of our Earth and crushing it, intensifying it beyond all reason. A magnetar's magnetic field is not just strong, it is a quadrillion times stronger. That is a 1 followed by 15 zeros. The environment this creates is one of pure, distorted physics. From a distance halfway across our Milky Way galaxy, that magnetic field would still be powerful enough to wipe the data from every credit card on Earth. It warps the very structure of reality around it, creating a zone where atoms are stretched into long, thin needles, but the true danger comes from instability. The crust of a magnetar, a crystalline lattice of iron nuclei, is under unimaginable strain from the magnetic forces twisting inside it. Occasionally, this crust cracks. This is a starquake, a seismic event on a cosmic scale. When it happens, the energy released is staggering. In a fraction of a second, a magnetar can unleash more energy than our Sun will emit in 100,000 years, all in the form of lethal gamma rays and X-rays. If one of these events occurred within 10 light-years of Earth, it could strip our planet's ozone layer, triggering a mass extinction. We are safe from such a catastrophe for now, but magnetars serve as a reminder that the universe harbors forces of such magnitude they can reshape matter and erase worlds from a truly astronomical distance. Magnetars demonstrate the raw power of a collapsed star, but there is another class of celestial object where the fury is more atmospheric, a constant churning rage. These are the brown dwarfs, the failed stars of the cosmos. They form like stars from collapsing clouds of gas and dust, but they never gather quite enough mass to ignite the sustained nuclear fusion that powers a true star. They exist in a cosmic twilight, too big to be considered planets, yet too small to truly shine. And within their deep, turbulent atmospheres, weather unfolds on a scale that makes Jupiter's great red spot look like a passing cloud. Imagine a world where the sky is not a gentle blue or a starry black, but a seething global cauldron. The heat within a brown dwarf, left over from its violent birth and from the slow crush of gravity, drives convection of immense power. Vast cells of hot gas rise from the depths, while cooler material sinks, creating planet-sized whirlpools and jet streams. These are not transient storms that last for weeks or years. They are permanent, continent-sized features locked in a perpetual, violent dance, and the clouds themselves are utterly alien. Depending on the brown dwarf's temperature, its atmosphere might be cool enough for water vapor to condense, but far too hot for it to be liquid. Instead, the clouds could be made of molten silicate droplets, essentially raining liquid rock. On hotter varieties, the clouds might be composed of vaporized iron, condensing into droplets that fall as a scalding metallic rain. This creates a meteorological environment of profound chaos, where the very sky is a fluid mosaic of molten minerals and scorching vapors, under a pressure that would crush any spacecraft in an instant. It is a realm of perpetual, violent twilight, where the storms are as permanent as the mountains on a planet, and the rain itself is a torrent of liquid stone. The chaotic skies of brown dwarfs are a symphony of churning matter, but there are places in the universe where the forces at work are far more absolute and infinitely more destructive. To approach a black hole is to enter a realm where gravity ceases to be a gentle pull and becomes a predatory force. The danger begins long before you cross the point of no return, the event horizon. It is a process with a disturbingly vivid name, spaghettification. This is the ultimate expression of tidal forces. Gravity weakens with distance, so the pull on your feet, if you were falling in feet first, would be vastly stronger than the pull on your head. The difference is not a gentle tug. Near a stellar mass black hole, this gradient is so unimaginably steep that your body would be stretched lengthwise with a force trillions of times stronger than Earth's gravity. You would not simply be pulled apart, you would be elongated into a single, thin strand of atoms, a human filament. The process would be horrifically swift. Every molecule, every bond that holds you together would be overcome in an instant. You would become a stream of elementary particles spiraling into the abyss. This is not science fiction gruesomeness, it is pure physics. The same fate awaits any form of matter, a gas cloud, an asteroid, or even an entire star that wanders too close. As the material is stretched, it heats through friction to millions of degrees, emitting a final, brilliant flash of X-rays as it is consumed. This tidal destruction is the black hole's way of preprocessing its meal, transforming complex structures into a simple, hot stream of plasma before it vanishes forever from our universe. It is a stark demonstration that in these most extreme environments, the very concept of an object of a coherent form is utterly meaningless. While black holes erase matter, other cosmic forces are endlessly creative, forging new landscapes in a relentless cycle of fire. Jupiter's moon, Io, is a testament to this creative destruction. It holds the undisputed title of the most volcanically active body in the entire solar system, a world so thoroughly heated from within that its surface is a constantly changing mosaic of molten rock and colorful sulfur deposits. This incredible activity has nothing to do with a hot core in the way Earth's does. Instead, Io is baked by the immense gravitational pull of Jupiter itself, along with the rhythmic tugs from its neighboring moons Europa and Ganymede. As Io orbits, this combined gravity stretches and squeezes the moon's interior, a process called tidal heating. The friction generated is so intense that it melts rock on a planetary scale, turning Io into a global pressure cooker of magma. The result is a surface unlike any other. Hundreds of active volcanoes dot its landscape, some spewing plumes of gas and ash hundreds of miles high, so tall they can be seen from spacecraft far out in space. But the most iconic features are the vast lava lakes. These are not small ponds, but calderas dozens of miles across, filled with a churning, bubbling soup of molten silicate rock. The lava here is so hot it glows with a fierce orange-red light, visible against the moon's mottled yellow and white terrain of frozen sulfur dioxide snow. In some lakes, the crust on the surface cracks and reforms in real time, like the skin on a pot of boiling pudding, offering a direct window into the inferno below. Rivers of lava flow across plains, and new mountains are built and destroyed on timescales of mere decades. Io is a world being remade before our eyes, a planetary canvas where the paint is liquid fire and the brushstrokes are volcanic plumes that stain the thin sky. It is not a planet with volcanoes. It is, in every sense, a volcano that became a world. The churning lava lakes of Io are just one spectacular feature in the vast, dynamic weather system that is Jupiter itself. Swirling within the gas giant's striped atmosphere is a storm so immense and so ancient it defies all earthly comparison. This is the Great Red Spot, a perpetual hurricane of staggering proportions. It is not a transient weather event, but a permanent, churning fixture. Astronomical observations, including detailed sketches from the 1600s, confirm this colossal anticyclone has been raging for at least 400 years. To stand at its edge would be to witness a maelstrom of incomprehensible scale. The entire planet Earth, all 7 continents and every ocean, could fit neatly inside this single storm. And within that vast expanse, the winds scream. They whip around the spot's oval perimeter at speeds exceeding 400 miles per hour, a velocity that makes the most powerful terrestrial tornado seem like a gentle breeze. But the true mystery of the Great Red Spot is not just its size or its age, but its energy. What could possibly fuel such an unending fury? The storm is a high-pressure system, a massive atmospheric mountain of gas that sits atop Jupiter's cloud decks, rotating counterclockwise. Unlike hurricanes on Earth, which are fueled by warm ocean water and quickly dissipate over land, the Great Red Spot has no solid ground to sap its strength. It exists within Jupiter's deep, turbulent atmosphere, a fluid environment thousands of miles thick. The storm likely draws its enduring energy from the planet's own internal heat, radiating upward from the depths and from the sheer chaos of Jupiter's jet streams, which constantly shear and interact with the spot's edges. It is a self-sustaining engine of wind, a vortex that has outlasted empires, feeding on the planet's own boundless atmospheric violence. It is a monument to meteorological endurance, a whirlwind that could swallow our world whole and has watched centuries pass as a mere moment in its long crimson life. The unending fury of the Great Red Spot is just a surface feature of a far more encompassing threat. Jupiter's true danger is invisible, a pervasive and lethal force that extends millions of miles into space. This is the gas giant's magnetosphere, a vast, teardrop-shaped bubble of magnetic influence that is the largest structure in our solar system. If you could see it from Earth, it would appear larger than the full moon in our sky. At its heart is a magnetic field nearly 20,000 times more powerful than Earth's, generated by the churning of metallic hydrogen deep within the planet. This colossal magnetic field acts as a cosmic particle accelerator of unimaginable scale. It seizes charged particles, electrons and protons from the solar wind, and even volcanic material blasted off the moon Io, and whips them to nearly the speed of light. Trapped within this magnetic prison, these particles form the Jovian radiation belts, zones of intense radiation that are millions of times more powerful than Earth's protective Van Allen belts. To venture into this environment is to enter a maelstrom of atomic violence. The radiation here is so intense it would deliver a fatal dose to an unshielded human in mere minutes. For our robotic explorers, it presents an engineering nightmare. The spacecraft Galileo, which orbited Jupiter in the 1990s, had to be fortified with over 300 pounds of special shielding just to survive long enough to complete its mission. Even then, its electronics were constantly bombarded, suffering memory errors and sensor degradation from the relentless particle assault. This invisible ocean of radiation doesn't just endanger visitors. It profoundly shapes the very worlds it engulfs. The moon Europa, with its promising subsurface ocean, is constantly bathed in this deadly rain. The radiation bombards its icy surface, breaking apart water molecules and creating potentially life-giving but also destructive chemistry. It creates a stained, fractured landscape and may even drive energy into the ocean below. Jupiter's magnetosphere is thus more than a magnetic field. It is a pervasive, energetic ecosystem of its own, a zone of pure particle fury that dictates the fate of everything within its gargantuan grasp. The pervasive radiation of Jupiter is a force of pure destruction, but on a distant, shrouded world, the chemistry of life may be assembling from an entirely different recipe. Saturn's largest moon, Titan, is a world cloaked in perpetual orange haze, a place where familiar landscapes are sculpted by alien liquids. Here, the rivers run not with water, but with liquid methane and ethane. The lakes that dot its polar regions are not filled with water, but with these same hydrocarbons, forming placid bodies under a dim, distant sun. Even the rain that falls from its thick, nitrogen-rich atmosphere is a frigid drizzle of methane. This creates a hydrological cycle of breathtaking strangeness, a perfect mirror of Earth's water cycle, but operating at a bone-chilling -290 degrees Fahrenheit. On Titan, methane is what water is to Earth. It evaporates from the lakes, forms clouds in the sky, and falls back as rain, carving river valleys and smoothing plains over eons. The Huygens probe, which landed on Titan in 2005, sent back images of a landscape that felt hauntingly familiar: rounded pebbles on a riverbed, hills and drainage channels. Yet it was all shaped by a liquid that on our world is a flammable gas. This thick, smoggy atmosphere, rich in organic molecules, is constantly bombarded by solar radiation, cooking up a complex soup of prebiotic chemistry. The surface itself may be covered in dunes not of sand, but of plastic-like hydrocarbons that have rained down from the sky over billions of years. In the profound cold, with liquid methane as the solvent and an atmosphere buzzing with organic reactions, Titan presents a second, parallel blueprint for how the building blocks of complexity might come together. It is a frozen, yet astonishingly active, laboratory for chemistry we are only beginning to understand. The frigid chemistry of Titan operates in a deep chill, but there is a place in the cosmos where cold is not just an absence of heat, it is an active, aggressive force. Drifting through the constellation Centaurus over 5,000 light-years away is the Boomerang Nebula, a cosmic ghost. This is the coldest natural place we have ever discovered in the entire universe. Its temperature hovers at a mere 1 degree above absolute zero, the theoretical limit where all molecular motion stops. That is -458 degrees Fahrenheit, even colder than the faint, leftover glow of the Big Bang itself that permeates all of space. This profound chill is the work of a dying star. The Boomerang is a pre-planetary nebula, a brief and beautiful stage in a sun-like star's final act. As the star exhausted its fuel, it shed its outer layers in a series of powerful pulses. But here, the process took a unique and extreme turn. The central star is expelling gas at a ferocious speed, blasting material outward at over 300,000 miles per hour. This rapid expansion is the key to the nebula's incredible cold. You can experience a miniature version of this principle with a simple aerosol can. When you spray the contents, the can gets cold. That is because the gas inside expands quickly as it exits, and that expansion requires energy. It draws thermal energy from the surrounding area, cooling it down. The Boomerang Nebula is this effect writ large across light years of space. The star's furious outflow is expanding into the surrounding void so rapidly that it acts as a cosmic refrigerator, actively chilling the gas to a temperature lower than the background of space itself. It is a pocket of ultimate cold, a freezing breath against the vast, lukewarm backdrop of the cosmos, a temporary monument to the physics of expansion and loss. But even the coldest reaches of space are punctuated by the impending fury of stellar giants. In the constellation Orion, a familiar shoulder star named Betelgeuse marks one of the most volatile environments imaginable. This is not a stable, steady star like our Sun. Betelgeuse is a red hypergiant, a dying star in its final, dramatic act. If placed at the center of our solar system, its outer atmosphere would swallow the orbits of Mercury, Venus, Earth, and Mars, extending nearly to Jupiter. Its scale is almost incomprehensible. Within this titanic sphere, the star is a roiling, unstable cauldron. Enormous convection cells, larger than our entire solar system, churn within it, carrying heat from the core to the surface in a violent, bubbling process. This creates an environment of profound instability. The star's outer layers are not a smooth, defined surface, but a seething, loosely held atmosphere, constantly shuddering with titanic convulsions. Periodically, this instability reaches a breaking point. Betelgeuse does not simply shine, it erupts. In colossal stellar outbursts, it violently ejects massive plumes of its own material, casting off clouds of gas and dust equivalent to many times the mass of our entire planet. These eruptions create a chaotic, dusty shroud around the star, a circumstellar environment of its own making. At times, this dust has even caused the star to visibly dim from our perspective on Earth, as if a cosmic veil were drawn across its face. Each of these violent episodes is a preview, a rehearsal for the star's ultimate fate. Betelgeuse is living on borrowed time, fusing heavier and heavier elements in a desperate, final struggle against gravity. When that struggle finally ends, the core will collapse and the star will detonate in a supernova of staggering brightness, outshining the full moon in our sky for weeks. The environment around it now, with its sporadic eruptions and dusty ejecta, is the prelude to that cosmic cataclysm, a dying star's final, turbulent breaths before the ultimate silence. While the surface of Venus is a crushing inferno, a strange and unexpected possibility floats high above the scorched plains. Some 50 to 60 kilometers up, within the planet's thick, yellowish cloud deck, the environment becomes almost, and we stress almost, hospitable. Here, the temperature and pressure are startlingly similar to those on Earth's surface. You could walk outside a pressurized craft without a spacesuit, though you would not want to take a breath. For these are not water vapor clouds, they are a perpetual haze of concentrated sulfuric acid, a corrosive mist that would dissolve flesh and metal with terrifying efficiency. Yet this acidic blanket is not a placid shroud. It is a dynamic, racing river of gas, Venusian winds super-rotating at speeds over 200 miles per hour, whip these clouds around the entire planet in just 4 Earth days, a phenomenon where the atmosphere itself circles the globe faster than the planet rotates. Within this ceaseless acidic hurricane, a profound mystery lingers. When observed in ultraviolet light, dark, patchy streaks appear in the clouds. Something is absorbing that UV light, but we do not know what. These unknown ultraviolet absorbers create the contrasting patterns we see in Venus's atmosphere, and their chemical identity remains one of the planet's biggest puzzles. This leads to one of the most provocative ideas in planetary science. Could this acidic aerial zone be a habitat? The conditions of temperature and pressure are right for liquid water droplets to exist, though they would be droplets of acid. Some extremophile microbes on Earth not only survive in acidic environments, they thrive in them. Furthermore, certain sulfur-based chemicals could, in theory, act as a sunscreen against the intense ultraviolet radiation. It is a staggering thought. Life, if it exists there, would not be on the surface but forever airborne, drifting in the perpetual winds of a global acid storm, a fugitive biology in the clouds of a hostile world. It is a testament to life's potential tenacity, suggesting that even in a place as hellish as Venus, a niche might be found not on the ground but suspended in a corrosive sky. The corrosive clouds of Venus challenge our very definition of a habitable zone, but on distant water worlds, the definition of water itself begins to break down. Deep within the mantles of large, ocean-covered exoplanets, water is forced into a state so alien it seems like a contradiction. This is Ice 7, a form of water ice that remains solid even while scorching hot. On Earth, ice is synonymous with cold. We see it in snowflakes, glaciers, and freezer compartments, but the phase of water, whether it is a solid, liquid, or gas, depends on both temperature and pressure. Ice 7 forms under pressures over 30,000 times greater than Earth's atmosphere, a crushing force found hundreds of miles beneath a global ocean's surface. Under that incredible squeeze, the water molecules are forced into a different, tighter crystalline structure. This structure is so stable that even if the surrounding temperature rises to several hundred degrees Fahrenheit, the ice does not melt. It remains a solid, forming a thick global layer of hot ice. Imagine a planet like Gliese 1214b with its supercritical fluid ocean on the surface. Deeper down, as the pressure mounts, that churning fluid would transition into a vast global sea of liquid water. And deeper still, where the weight of the entire ocean above presses down, you would hit a boundary. Here, the liquid water meets the mantle, but it does not touch rock. Instead, it meets a floor of solid, hot ice 7. This hot ice layer could be hundreds of miles thick, a strange, rigid shell encasing the planet's rocky core. It is a geological intermediary, a frozen barrier born from unimaginable pressure, separating a sunless sea from the furnace of a planet's interior. In these extreme environments, the most common substance in the universe wears a mask we would never recognize, proving that even the familiar becomes profoundly strange under the right, or rather the wrong, conditions. The pressures that create hot ice are immense, but they are nothing compared to the forces unleashed by the universe's most powerful engines. At the heart of certain galaxies, supermassive black holes are not just passive consumers. They are active, ravenous dynamos. In these so-called active galactic nuclei, vast rivers of gas, dust, and even entire stars spiral inward toward the event horizon, forming a superheated, churning disk of doomed matter. This accretion disk glows with the heat of 1 billion suns, a blinding maelstrom of plasma. Yet not all of this material is destined to be swallowed. In a feat of cosmic engineering that we still do not fully understand, some of the infalling matter is seized by the black hole's immense magnetic fields and spun outward, not in a messy explosion, but in 2 perfectly focused opposing beams. These are relativistic jets, and they are the most powerful particle accelerators in existence. the plasma within them is accelerated to velocities so close to the speed of light that the laws of relativity dramatically warp their behavior. From our distant perspective, these jets can appear to move faster than light itself, an optical illusion caused by their near-light speed travel almost directly toward us. They blast through the fabric of their host galaxy and scream out into the intergalactic void, stretching for tens or even hundreds of thousands of light years. That is a distance far greater than the entire width of our Milky Way. Where these jets plow into the sparse gas that lingers between galaxies, they create colossal, glowing lobes of radio emission like titanic bruises on the cosmos. The energy they deposit is so vast it can heat entire galaxy clusters, preventing cool gas from coalescing and literally shutting down star formation for eons. A single jet from one of these active hearts can sculpt the future of thousands of galaxies around it, a testament to a force that can reach across millions of light years to impose its will on the universe. This invisible ocean of radiation is a constant dynamic force, but it originates from a source of seemingly empty tranquility. The void between planets, between stars, is not truly empty. It is filled with a near-perfect vacuum, a realm where a single atom might travel for miles before encountering another. Yet even here, in this profound emptiness, there is a relentless, energetic wind. From our Sun's turbulent outer atmosphere, the corona, a torrent of charged particles is constantly blasted outward in all directions. This is the solar wind, a supersonic stream of electrons and protons racing into space at speeds of over 1 million miles per hour. It is the Sun's breath, extending its influence far beyond the orbits of the planets. This wind carves out a vast protective bubble around our solar system called the heliosphere, a shield that helps deflect some of the more dangerous cosmic rays from interstellar space. But within this bubble, the solar wind is a sculptor. It presses against planetary magnetic fields, compressing them on the sunward side and stretching them into long, comet-like tails on the side facing away. Where this wind encounters a planet with a magnetic field like Earth, it is funneled toward the poles. There, the particles collide with atmospheric gases, sparking the ethereal, dancing curtains of light we call the auroras. It is a beautiful side effect of a constant, invisible bombardment. For worlds without a strong magnetic shield like Mars, this wind has been a thief over eons, slowly stripping away the atmosphere molecule by molecule. And for astronauts venturing beyond Earth's protective magnetic embrace, the solar wind represents a serious, ever-present hazard. A sudden surge from a solar storm can deliver a dangerous dose of radiation, requiring shelters with thick shielding on spacecraft and bases. So space is never still. It is a dynamic highway for this ceaseless, invisible gale, proving that even in the deepest vacuum, the universe is alive with energetic flow. That ceaseless solar wind is a river of time as well as particles, but near a black hole, time itself begins to falter. Gravity, as Einstein revealed, is not just a force pulling on objects. It is the curvature of spacetime itself. The stronger the gravity, the more severely spacetime is warped, and this distortion has a profound effect on the very fabric of time. Imagine you are an astronaut on a mission to orbit a black hole, maintaining a safe but close distance. You are equipped with a powerful flashlight, and you agree to flash it once every second by your own clock, back to a colleague observing you from a great distance. As you descend into the black hole's immense gravitational well, something bizarre happens from your colleague's perspective. The interval between your light flashes begins to stretch. First it is 2 seconds, then 10, then a minute. Your movements from their point of view appear to slow to a crawl. As you inch closer to the point of no return, the event horizon, your image would appear to freeze entirely. To the distant observer, you would never quite cross that final threshold. Your last flash of light would be stretched into an infinite, fading red smear across their instruments. This is gravitational time dilation, an environmental effect so extreme it warps reality itself. Yet your own experience would be utterly different. For you, inside your spacecraft, time would feel perfectly normal. Your heart would beat at its usual pace, your clock would tick 1 second per second. You would cross the event horizon in a finite amount of time, unaware of the frozen eternity you have become to the outside universe. This is not an illusion or a trick of light. It is a fundamental property of our cosmos. In the most extreme gravitational environments, time becomes a relative experience, a personal measurement that can diverge completely from the rest of existence. The black hole's grip is so powerful it can stretch a single moment into forever. Yet the birth of a planet is not a gentle event. It begins in a violent, dusty whirlpool surrounding an infant star, a chaotic construction zone on a cosmic scale. These are protoplanetary disks, vast, flat rings of gas and dust that orbit young stars like Saturn's rings, writ large across an entire solar system. Within this swirling maelstrom, the raw materials for future worlds are churned in a turbulent dance. The environment is one of constant, low-speed collisions. Microscopic dust grains, finer than flour, drift and bump into one another, held together by static electricity and molecular forces. Over thousands of years, these specks stick together, growing into pebbles, then boulders, and eventually mountain-sized bodies called planetesimals. This is not a serene process. The disk is a dynamic, stormy place. Turbulent eddies of gas, like giant whirlwinds, sweep through the material, and subtle variations in pressure create zones where dust and pebbles get trapped, piling up like cosmic traffic jams. These pressure bumps become the nurseries for planet cores, allowing material to accumulate faster than it can be scattered. Gravity then takes over, pulling these growing clumps together in violent mergers, sometimes shattering them, other times fusing them into the embryonic hearts of future worlds. It is a dusty, violent, and incredibly beautiful arena, a place of both creation and destruction where the gentle orbits of tomorrow's planets are forged in the chaos of today. But the ultimate strangeness of a neutron star is hidden deep within its core. Beneath that iron crust, in a realm of such density that atomic nuclei dissolve, matter enters a state of pure quantum madness. The intense pressure forces protons and electrons to merge, transforming almost the entire star into a sea of neutrons, and in the deepest, coldest layers of this sea, something astonishing happens. This neutron-rich material may become a superfluid. Imagine a liquid with absolutely no internal friction, no stickiness at all. If you could stir a cup of this superfluid, it would swirl forever, never slowing down. It defies everything we know about how fluids behave. This frictionless state is only possible under the extreme cold and density inside the neutron star, where quantum effects dominate on a macroscopic scale. The entire interior could be flowing in complex, eternal currents without losing a single bit of energy to heat. This quantum ocean has a direct and violent effect on the star itself. Neutron stars are the universe's most precise clocks, spinning with a regularity that rivals atomic timekeeping. But sometimes they stutter. In an event called a glitch, the star's rotation suddenly speeds up by a tiny but measurable fraction. For decades, these glitches were a profound mystery. How could a billion-ton ball of solid nuclear matter suddenly spin faster? The answer likely lies in that internal superfluid. The outer crust of the star, the solid part we see, is locked in a specific spin, but the superfluid interior beneath it may rotate at a slightly different speed. Think of it like an egg. The solid shell is one piece, but the liquid yolk inside can slosh independently. In the neutron star, the frictionless superfluid can essentially spin on its own. As the star ages and its crust slows down very gradually from emitting radiation, the superfluid core may not slow down as quickly. Eventually, the difference in rotation builds up too much strain. The two components suddenly couple together again, transferring angular momentum from the fast-spinning superfluid to the slower crust. This transfer gives the crust a sudden kick, speeding up its spin in a fraction of a second. This event can also trigger starquakes, where the rigid crust cracks and shifts to accommodate the new internal motion. These glitches and quakes are more than just celestial curiosities. They are our only window into the bizarre quantum ocean sloshing inside these stellar corpses, a direct signal from one of the most extreme states of matter in the cosmos. This quantum sloshing within a neutron star is a whisper from a different kind of extreme, a reminder that the universe's most bizarre physics often hide in plain sight. But there is one environment so vast and so fundamental that it is easy to overlook entirely. It is the cold echo of creation itself, the cosmic microwave background radiation. This is not a place you can point to on a map of the sky. It is the map. It is the oldest light in existence, a faint glow that permeates every single cubic inch of the observable universe. Roughly 380,000 years after the Big Bang, the universe had expanded and cooled enough for the primordial soup of charged particles to finally combine into neutral atoms. In that moment, the cosmos became transparent for the first time, and light was set free. That first flash of light has been traveling ever since, stretched by the expansion of space over 13.8 billion years from visible, blinding brilliance into the microwave part of the spectrum. Today, it bathes everything in a uniform, icy cold bath of radiation, corresponding to a temperature of just 2.7 Kelvin, or about -455 degrees Fahrenheit. This is the ultimate baseline, the cold fossil from the universe's most violent and energetic beginning. Every star, every galaxy, every black hole we have discussed exists against this silent, frigid backdrop. It is the afterglow of the most extreme environment of all, the furnace of the Big Bang, now cooled to a whisper that still tells the story of everything. That ancient cosmic whisper provides a baseline of cold, but within our own solar system, a world exists where that chill is combined with a relentless, sterilizing glare. The surface of Mars today is a masterclass in hostile evolution, a landscape that has been stripped, scoured, and frozen into a state of profound desolation. While it once boasted rivers and lakes billions of years ago, the modern Martian environment is a cautionary tale of a planet that lost its protective shield. The core of the problem is its atmosphere, or rather, the devastating lack of one. The Martian air is over 100 times thinner than Earth's, a wispy veil of carbon dioxide that offers almost no protection from space. This thin blanket fails to trap heat, leading to average surface temperatures around -80 degrees Fahrenheit, with swings that can plunge even lower at night. But the cold is only part of the story. With so little atmosphere to block it, the surface is bathed in a constant, lethal flood of ultraviolet radiation from the sun. On Earth, our ozone layer absorbs most of this DNA-destroying light, but on Mars, it rains down unimpeded. Any unprotected organic molecule on the surface is quickly broken apart by this energetic assault, which is one reason finding evidence of past life there is so challenging. The radiation acts as a constant planetary-scale sterilizing agent. Then there are the dust storms. Martian dust is fine as talcum powder and charged with static electricity. When winds pick up, which they do with surprising force in the thin air, they can lift this dust high into the sky, triggering storms that start regionally but can rapidly grow to engulf the entire planet. These global events can last for months, blotting out the sun and turning the sky a hazy, oppressive pink. They coat every surface, choke solar panels, and dramatically alter the planet's temperature. This combination creates a hyper-arid, freezing desert under a deadly sky. The soil itself is not just dry, it is chemically hostile, rich in perchlorate salts that are toxic to most life forms and can break down organic matter. For life as we know it, the Martian surface is a multi-front war of attrition. It is freeze-dried, irradiated, poisoned, and periodically buried in global dust. It stands as a stark lesson in how a world can change, losing the elements that once made it soft and welcoming, transforming into a monument to the relentless, abrasive forces of cosmic weather. The desolate surface of Mars shows us a world stripped bare, but deep within the ice giants we met earlier, a final, theoretical frontier of matter awaits. Beyond the diamond rain in their atmospheres, in the mantle layers of Uranus and Neptune, scientists believe water is forced into a state that defies all our everyday logic. This is not Ice 7, the hot solid we discussed. This is something stranger, a phase of matter that exists only in the most extreme laboratories on Earth and in the hearts of these distant worlds. They call it superionic water. To create it, you need conditions of almost unimaginable violence, temperatures of several thousand degrees Fahrenheit, and pressures over 1 million times greater than Earth's sea level. Under this brutal combination, the familiar water molecule, H2O, is literally torn apart. The oxygen atoms, robbed of their hydrogen partners, are squeezed into a tight, rigid crystalline lattice like the scaffolding of a solid. But the hydrogen ions, now just single protons, are set free. They behave like a liquid flowing effortlessly through the solid oxygen cage like a current of charged particles. Imagine a block of ice that is also an electrical conductor, where part of the structure is fixed and the other part is a rushing river of charged particles. This bizarre hybrid is not a solid, nor a liquid, nor a gas. It is a distinct state of matter, a hot, dense, electrically conductive ice that could explain one of the great mysteries of the ice giants, the source of their unusual and lopsided magnetic fields. Unlike Earth's relatively tidy magnetic field, which is generated by the churning of molten iron in its core, the fields of Uranus and Neptune are messy, multipolar, and oddly offset from the planet's centers. A global shell of superionic water in their mantles, with its freely flowing hydrogen ions, could act as a dynamo, generating these chaotic magnetic fields from a layer far above the core. So within these blue worlds, the most common substance in the universe may become a planetary-scale electrical circuit, a seething, conductive layer that shapes the very magnetic soul of the planet. It is a fitting final fact, a reminder that even after 25 glimpses into cosmic extremes, the universe holds layers of mystery within layers, where the ordinary becomes extraordinary under the right, or rather the truly unimaginable conditions. From superionic ice to the afterglow of creation itself, we have journeyed through a gallery of cosmic nightmares and wonders. We have stood on worlds where oceans boil under alien suns, where diamonds fall like rain, and where the sky itself is an eternal, corrosive storm. We have witnessed stars flung from the galaxy, black holes that stretch time into a smear, and the silent, frozen arcs drifting in interstellar night. These are not just distant curiosities, they are the universe operating at its most raw and unrestrained, pushing the very laws of physics to their breaking point and often beyond. Each extreme environment is a natural laboratory, revealing what matter and energy can do when freed from the gentle constraints we enjoy here on Earth. They challenge our definitions of what is possible, of what is normal, and even of what is alive. This breathtaking diversity, from the quantum slosh inside a neutron star to the planet-swallowing storm on Jupiter, teaches us one profound truth. Our pale blue dot, with its temperate climate and protective sky, is not the standard model for a world. It is the rare exception, a fragile oasis of calm in a cosmos that is overwhelmingly, magnificently hostile. These extremes define the universe, not our quiet corner of it. They show us the incredible range of conditions under which the cosmos operates, and in doing so, they redefine our own place within it. We are not at the center of anything but our own experience. We are inhabitants of a single, precious point of mildness in a sea of ferocious beauty. So tell us, which of these extreme facts left you the most awestruck? Was it the rogue planet with its hidden ocean, or the magnetar whose invisible field could erase our technology from half a galaxy away? Share your thoughts below, and if you want to continue exploring the universe's greatest mysteries, be sure to subscribe. Our next adventure into the unknown is always just one click away.